Hello everyone and welcome to the OneClass channel. My name is Donna Riel and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then check out the links in the description below. So now let's get started on our set of questions for today's session. Okay, so question 1 says to write Lewis structures for CO32-, HCO3-, and H2CO3. When acid is added to an aqueous solution containing carbonate or bicarbonate ions, carbon dioxide gas is formed. We generally say that carbonic acid, H2CO3, is unstable. Use bond energies to estimate delta E for the reaction in the gas phase. Specify a plausible cause for the instability of carbonic acid. Okay, so the first part of the question asks to write all the different Lewis structures for all these different ions. So let's start with carbonate ion, CO3 2-. So to find the Lewis structure of anything, we need to find first the total valence electrons of the compound. So for carbon, it has 4 valence electrons. For oxygen, there are 6 valence electrons. And since there are 3 oxygen atoms, I'm going to multiply this by 3, which gives us 18. And then finally, there's a -2 charge on the compound. So we are going to add an additional 2 electrons. So in total, this gives us 24 valence electrons. So now I'm going to start off by writing my carbon in the middle. Let's do a different color. Let's write my carbon in the middle. And then I'm going to draw my 3 oxygens, all single bonded. Okay, so let's recall that for every single bond, there are 2 electrons participating. So far I've drawn 6 out of the 24 electrons that I should have. So now I'm going to then draw all of the lone pairs on oxygen. So each of them contain 3 valence electrons. And now let's count it out. These will all have negative charges as well. If we counted out how many I have drawn now, each oxygen has 1, 2, 3, 4, 5, 6 valence electrons. There are 2 electrons in every bond, so that's 8 times 3. So I've drawn 24. But if you look at our central carbon atom, you'll notice it doesn't have a full octet. So what we need to do now is form a double bond. And to do that, I can show one of the oxygen's negative charge come down to form a double bond so that our carbon has a full octet. So now we can draw out pretty much the same thing. Except now there is a double bonded carbon, oxygen bond, and only 4 valence electrons on that oxygen. Okay, so now let's double check that we have our 24 electrons, 1, 2, 3, 4, 5, 6, 7, 8, plus 8, 16, plus another 8, 24. Okay, so the correct Lewis structure I will box in green for the carbonate ion. So now let's do the same thing for one of the bicarbonate ions, HCO3 minus. Let's find its total valence electrons. Carbon is 4. Oxygen, 6 times 3, which is 18. And then this ion only has one -1 charge, so I'm going to add 1 electron. And what I also need to write is that there is a hydrogen which has 1 valence electron as well. So this will also give us a total of 24 valence electrons. So this is pretty similar to our first ion, which makes sense because it just has a proton added. So I know I'm going to need a double bonded oxygen. This carbon will be bonded to 2 oxygens, except this time one of the oxygens will contain a hydrogen. So this is now the structure for HCO3 minus. And let's double check the number of electrons. We have 1, 2, 3, 4, 5, 6, 7, 8, plus 16, 17, 18, 19, 20, 21, 22, 3, 24. Okay, so this is the Lewis structure of HCO3 minus. Okay, so now let's do carbonic acid. Carbon, 4 electrons. Oxygen, 6 times 3. Hydrogen, there are 2 this time, so it's 1 electron times 2. So the total valence electrons is 24 again. Okay, so I'll draw here. There will be a double bonded oxygen to the carbon, and it is bonded, single bonded to 2 oxygens. And then each of those oxygens has a hydrogen attached. Okay, so now I'll just draw all of the lone pairs that are missing. And this is our final Lewis structure. So we can double check and count out all the electrons. 4, 5, 6, 7, 8, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, so this is the final Lewis structure for carbonic acid. Okay, so now that we have all the Lewis structures written down, we can get to the second part of the question. I'll just label it as 1B. So I'm going to first draw out the chemical reaction. So this was already given in the question. And it might be easier to just show this reaction and also showing all the bonds and the reactants and the products. So we know from the previous step what the Lewis structure of carbonic acid is. And the structure for carbon dioxide is just carbon double bonded with 2 oxygens. And the Lewis structure of water is just oxygen with 2 lone pairs. Okay, so this is just pretty much showing the reaction with all of the different structures. So when we want to use bond energies to estimate delta E for the reaction in the gas phase, it's easier to just make a table showing all the different bonds that are broken and formed. So we have 3 types of bonds for all 3 of these different molecules. So we have a single bonded carbon and oxygen as one of the bonds. There's also a double bonded carbon and oxygen bond. So this is in carbonic acid and also in carbon dioxide. And there is also a single bonded oxygen to hydrogen bond as well. Okay, so that's one of the columns. The second column will be the energy of all of these types of bonds. So this might be given in the question, but I'm going to Google just a bond energy table. Yes. Okay, so let's just try to find one of them. Let's use this one. It's kind of clean. Okay, so using this table, a carbon-oxygen bond has an energy of 358 kilojoules per mole. A double bonded carbon-oxygen bond, 805 kilojoules per mole. And then a single bonded oxygen-hydrogen is 464 kilojoules per mole. Okay, so that is our second column in this table. And what I also want to write down are the number of reactant bonds for each of these bonds in the table. So we just need to count out how many single bonded carbon-oxygen bonds there are in our reactant. So if we count it out, we'll see that there are 2. How many double bonded carbon-oxygen bonds in the reactants? So there is only 1 in carbonic acid. And lastly, how many oxygen-hydrogen bonds there are? There are 2 as well. And then let's do the same thing for our number of product bonds. So now let's look at carbon dioxide and water. So how many single bonded carbon-oxygen bonds? There are none. How many double bonded carbon-oxygens? There are 2 in carbon dioxide. Lastly, how many single bonded oxygen-hydrogen bonds? There are also 2, and they are in water. So now we need to find delta E for the reaction. So that just means like delta energy, but I can also denote it as delta H. See what they use. Yeah, I'll just use delta H. So delta H is equal to the sum of your delta H of formation of all of the broken bonds so all the bonds that need to be broken are from our reactants, so from the carbonic acid. And this will be minus the sum of the delta H of formation of all of the formed bonds. So all of the bonds needed to be formed in the products. Okay, so now I can sub in all of the energy values and then show how many of those bonds are broken and how many are formed. So that's why it was helpful to write out the table. So let's look at all of the broken bonds. There are 2 single bonded oxygen bonds that were broken in our reactants. Those going to be 2 times 358 kilojoules per mole, but I won't write the units in for now. And then another bond that was broken was the carbonyl bond. So there is only 1 carbonyl bond, so we're going to add 805. And then there are 2 alcohol bonds that were broken. So it's 2 times 464. So those are all the broken bonds. And now I'm going to minus the sum of all of the bonds that were formed. So it is just the 2 carbon double bonded with oxygen bonds. So 2 times 805 plus the 2 OH bonds that were formed. 2 times 464. And those are all of our formed bonds. So if we add it all up, you get 2,449 minus 2,538, which is equal to negative 89. Yeah, negative 89 kilojoules per mole. So the last part of the question just asks, specify a plausible cause for the instability of carbonic acid. So the instability of a reactant depends on how stable the products it forms are. So if we look at both carbon dioxide and water, these are both stable. So this might help us kind of justify the fact that carbonic acid is unstable, because once it forms carbon dioxide and water, since these 2 products are stable, it's not likely they're going to react again to form carbonic acid. This might be a reason why carbonic acid is unstable. Okay, so now let's see what the junior tutor said. Going back to my previous page, they have the different probable Lewis structures of the carbonate ion. Okay, so they have all of the different resonance structures. So all of these are correct. So mine is the most similar to the first one that they drew. They have the bicarbonate ion. Yep, so any of these is correct. They have both the resonance structures. And then lastly, they have the Lewis structure for carbonic acid, which is the same as mine, so that is correct as well. Part B, they wrote out the helpful table to help solve delta E 358, 803, 464. So it depends on what book you use as a reference. So the table that they had has 803 instead of 805, but it's pretty similar. So depending on what you use as a reference, you might get slightly different values. They counted out the number of reactant bonds and the number of product bonds. And then they did the delta H, which is the sum of the delta H of formation of the energies of broken bonds, and then the sum of the delta H of formation of all the bonds formed. And they got negative 87 kilojoules per mole. So when H2CO3 decomposes, it forms two very stable compounds, carbon dioxide and water. That's why it's unstable. Yeah, so that's kind of what I said too. So this solution is correct.